Axioms, interpretation, and properties of probability. So these axioms are the basics in this probability. On top of that, we define probabilities. Let's say probability theories. So let's see what are those things. We just talk about only few basic axioms and probability theories. We are not going much deeper. Okay, probability. Probability mean chance that an event will occur. Okay, it's a chance to happen an event, particular event. So uh, to tell the probability of this, first we need to define what is the event. Then we can tell, okay, this is the probability of this event. Clear? So probability value always in between 0 and 1, including 0 and 1. Okay. You can calculate your probability. Probability we defined by capital P. That's the letter probability of event. Okay, that's how we. That's what I mentioned here. Capital P within brackets, capital A. A is the event here. Okay, so probability of what? That event should be inside the bracket. Okay, it is equal to the number of outcomes in that particular event divided by total number of outcomes. Okay, it is very similar to relative frequency, if you remember. So you will see later they are like equal. Okay, clear? Number of outcomes in event A divided by total number of outcomes in event B. Those are numbers, those are values. Okay, n of A and capital N, those are numbers. Okay, basic properties of probabilities we can write like this: probability of an event, capital P of A, definitely greater than or equal 0. Okay, greater than or equal 0, but less than or equal so less than or equal 1. Okay, I haven't mentioned it here. Total probability, we call this axiom 2, which is something like total probability. Probability of entire sample space is 1. It is possible, right? If I have 10 events, probability of happen these 10 events is 1, something like that. Axiom 3, which is if we partition our sample space, let's say suppose that we have these partitions A1, A2, A3 up to, I don't know, infinite partitions. If we have this, let's say, if we have, okay, this is my sample space. So I have partitioned my sample space like this up to infinite numbers. Like this is my A1, this is my A2, okay, like that. So if this is an infinite collection, okay, the infinite collection of what? This is important. Infinite collection of disjoint events. They don't have common space. Okay, they have nothing in common. Each, if you consider each event, each partitions, they have nothing in common. Probability of union of these events you can denote by summation, the summation notation. Okay, sum of sum from I equals 1 to infinity probability of AIs, probability of these partitions. Okay, which mean PA1 plus PA2. Okay, this probability of A, or let's say probability of within bracket A, normally I call PA, something like that. Okay, It's easy. So simply you can rewrite this: probability of A1 plus probability of A2 plus infinity, probability of whatever. Okay, clear? Okay. Any event, if you consider an event, as I mentioned, probability of that event definitely greater than or equal 0, less than or equal 1. Okay. So if you remember, we talked about complement of an event. Complement, which means not that event. Okay. So probability of that particular event plus probability of complement of that event equals to 1. It's possible, right? It's obvious. So it is mentioned here: A and A dash. A dash mean complement event. So probability of, let's say, if I have, this is my capital A, complement is this one, this space, right? So probability of A plus probability of A dash equals to probability of S, which means sample space, right? So it is 1. So this probability of capital S, that's why it's equal to 1. Okay. So you can just do some like subtract probability of A from left hand side and right hand side. You can get the next equation, like probability of A dash equals 1 minus probability of A. Okay, this is very very important result. Where is my pointer? Sorry, this is very important result. If you know what is the probability of A, you can simplify probability of A dash by using this. Okay. Okay, propositions. Addition rule. This is something very important. This addition rule. If we have two events, A and B, let's say A and B, probability of union of those two events, probability of A union B, you can simply write probability of A plus probability of B plus, minus probability of their intersection. Why this happens, I can show you simply using, let me using this Venn diagram. This is my A, this is my B. Okay, this is B, this is A. Okay, so I need probability of A. Sorry. I need probability of, this is my A, this is my B. Sorry for that. A. I need probability of A union B. Okay, which means everything inside these two circles, right? But okay, what is probability of, sorry for this line, what is probability of A, which means this piece, right? What is probability of B? This piece, including this intersection as well. So once you consider these two, summation of these two, what happened? You have counted this piece twice, right? For the probability of A and the probability of B. That's why we had to remove just one. Remove one part from this, which means probability of A intersect B. Clear? That is in this addition rule. Okay. 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 You can extend this addition rule to any number of events, like 3 events, 4 events, doesn't matter. So only thing is you have more number of things to calculate. Like if you consider this for 3 events, probability of A union B union C, then individual probabilities minus probability of two intersections, like probability of negative minus probability of A intersect B minus probability of A intersect C. Okay, and the other two combination of these, all these three, minus probability of B and C. Okay, then plus their intersection. See, this one and this one, they are quite similar, but you can see last part, it is different. Sorry, it is different from the two event addition rule, right? Two events addition rule, it is different. So you can simply draw a Venn diagram and check why this happens. Okay. 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 Let's say A and B are mutually exclusive, which means they are separate events. Okay, mutually exclusive. They have no common space. At that time, this last piece goes to 0. Why? Because they don't have any common space. Okay, that's why I have mentioned here in this case, if we have A and B mutually exclusive, then you can calculate probability of A union B simply by taking their individual probabilities. Okay, clear? Which means probability of A intersect B is 0. Okay. Let's check this example. We have a deck of cards. There are 52 cards. Each category has 13 cards. Okay, they have picture cards and non-picture cards as well. So altogether we have 52 cards. Event A. Where's event A? What is event A? Selecting a red card. That's my event A. Selecting a red card. So it doesn't matter whether it is a picture card or not. Selecting red cards, which means one of these, right? Altogether there are 26 red cards. Okay, 26. So for this event A, how many number of occurrences? 26. Okay, altogether we have 52. So anytime you need to find the probability of A, which means equals to 26 over 52, right? I don't know whether we need to find it. Yeah, what is PA? So it is 26 over 52. Same here, same thing in part B. It is B. Your probabilities, it depends on, okay, your probability, it depends on how you define your event. That's very important, okay? That's definitely depends on your, how you define on your event. So B, picking a diamond card. In this event, we haven't mentioned any color, only diamond cards. Okay, so you have to find how many diamond cards here and divide that from total number of occurrences to find the probability of B. Okay, so diamond cards, how many? 13, right? 13. So 13 divided by 52. Clear? Okay, I'm not going to do the other two. C, picking a king card. So there are only 4 kings, right? So in this page, you can find the answers. Okay, clear? This is how we find. Normally we don't, right now it's fine, but normally we try to simplify these fractions. Okay, normally we give probabilities like decimals. Okay, 0.5, 0.1, something like that. Okay, since you are using calculators, it is easy, no need to worry about that. Okay. Okay, this example, PA, PB, and PA union B, those are given. So what you need to find is probability of A dash, probability of B dash, probability of A intersect B. It is easy to find first two. Why? Because given PA and PB. So you know PA dash is 1 minus PA. Okay? PA means probability of A. Clear? So plug the values, find PA dash. Same for the PB dash. Once you need to find A probability of A union B, then what you have to do? Apply the addition rule. Okay. So you know these values, PA given, PB given, and intersect given. Okay. Plug the values. Just simplify a little bit, and you can get the answer. Chapter 2.3, it is an optional chapter, subsection. It is about counting. Okay, countings like combinations counting. If we have a number of let's say I have a number of pens. Okay, I have a number of pens. I need to pick two. So what is the probability of picking two pens? Something like that. Okay, that subsection 2.3 based on countings, but it is optional case. If I have enough time, I'll do it. Okay, so if you need to check it, you can check. Notes are there. I think I have already uploaded those notes. So if you need, you can check it, or if you have any questions, you can email me and ask. Okay, from that part 2.3. Clear? I'm not going to ask any question from 2.3 for the mid exam, so final exam. Okay, optionals are just optional. I'm not going to ask any question from that. Okay, 2.4. This is very important. Conditional probability, which means we have already given something and we need to find the probability of a particular event which exists on top of that given event, something like that. So I'll show you that. Okay, this is the idea. Let's say if you have your partitions. Okay, these are the partitions in my sample space. Okay, so let's say I have this partition. This is AK, partition number AK. This is A1, A2, likewise. Okay, so I have an event called event B. It is this one. My event is event B. Okay, so I define my event on top of this partition. Okay, so now I need to know what is the probability of B given AK. AK is an event. Okay, AI, A1 event, A1 is an event, A2 is event, all are events. So I need to find what is the probability of B is given AK. Clear? Something like that. Conditional. Check this. I think this, yeah, definition. Two events, A and B. Probability of A given B, probability of A, B already given. Okay, probability of A given B defined by probability of A given B. Okay, this sorry, this symbol, it is not the this one, it is not the division. Okay, or it's not a slash, it is just a line. Okay, that's what we call given. So whatever given, always in the right hand side of that particular line. Okay, so this is like this. See, A, this is the event, and this is the given part. B is the given part. It's already given. Okay, so you can find it by using this equation. Probability of their intersection divided by probability of given event. Probability of given event. Okay. This one. Probability of B. Okay. Don't change the order. Okay. Always the probability of their intersection divided by probability of given event. Okay. So since we have a division divided by probability of B, division denominator always greater than 0, right? Otherwise it is undefined. That's why we have mentioned probability of B definitely greater than 0. If it is 0, then we have a problem. Okay, that's why probability of B always greater than 0. In the same way, you can define vice versa. Probability of B given A. What you have to do, just change the events. Same thing, probability of A intersect B divided by what is given. Now A is given, so probability of A. Okay. This place I'll tell you, if you need to do some math here, you can simply cross multiply. Probability of B given A multiplied by probability of A equals probability of A intersect B. Clear? Just cross multiply. Okay, then you can isolate any term and do your calculations. You will need that later. Okay, clear? This is we call conditional probability, and this is I think really important in general. General we are doing statistic stuff. Okay. Okay. This is a simple example. Factory has defective and non-defective items in 3 lines. There are A, B, C lines, 3 lines. Okay, what we need to find? Okay, there are so many things need to find. PD, PA, PC. So A, B, C are lines. D is defective. N is non-defective. Okay. Okay, what is PD? Probability of D. D means defective. Simply defective. So how many defectives are there? This one. Total 62 defective items. Okay. Total number of occurrences, which means total we have 3000. Okay. So 62 divided by 3000 gives us probability of D. Probability of defectives. Okay. Same thing you can find individual cases PA, PB, PC, PN. Okay. This one. Just check this one. Probability of D intersects C. D and C. So probability of D and C. What is D? This line. Right? What is C? This line. Okay. So what is the intersection? Oh, sorry. This one. Right? So 25 is the common area what what they have. So 25 divided by total number of occurrences, 3000. Clear? Now, conditional part. If C is given, I need to find D. So probability of D given C. So given part always comes to the right hand side. So probability of D given C. Simply apply your equation, which means probability of D intersect C divided by probability of given event. Here it is C. So probability of C. I think you already know these pieces. Yes, probability of D intersect C. You can find here this one. Probability of C, yes, given. So plug the values and simplify a little bit. Okay, clear? Okay, this example, yes, check this one. Given probability of A, given mean you have given probability of A, probability of B, and conditional probability. Probability of A given B. So you need to find B given A. First, write down what is this, okay? Which means probability of B intersect A divided by given event, probability of given event, which is A, okay? Do you remember last day I told you something about commutative law, which means you can interchange the order of the events, okay? So simply you can uh, change the order of this event, which means probability of, you can write it A intersect B divided by PA. Clear? Can simply interchange them. Okay. Okay. Uh, do you have probability of A intersect B or B intersect A? No. So how do you find that? Uh, you have given, you have been given which one? This one. Probability of A given B. So write your equation for that. Probability of A given B. Probability of A given B, which means probability of A intersect B divided by probability of, now it is B. Okay. So A given B, it is given here. Okay. So you know this piece. You don't know this guy, but you know this one. Okay. From unknown three values, you know two of them. So cross multiply PA given B times PB. Then you can isolate this unknown part, probability of A given B. Sorry, probability of A intersect B. Sorry, okay. So find that value and simply you can plug that value here. You know this one, now you know this one, then easily you can find what they ask. Okay, clear? This is how we deal with this kind of conditional probabilities or probabilities. Okay. So it is mentioned here, those process, these steps I am explained there. Clear? Okay. Questions? Yes. Oh, you mean this one? Yes. This one? Oh, this is cross multiplication. Okay. Just multiply both sides by probability of B. Something like this. See, this one cancel with this one, but you have A intersect B, probability of A intersect B, something like that. Okay, clear? Okay. Then you have your answer. Yes, that piece we have in a separate part we call sorry, multiplication rule, because we cross multiply them. Okay, which means you can simplify probability of A intersect B by using probability of A given B times probability of B. Okay, so you got this from A given B, probability of A given B equals probability of A intersect B divided by probability of B. Cross multiply them and you have this answer for probability of A intersect B. Okay. In this example, I think it's a DVD. It's about DVD players. Okay. 50% are brand 1, 30% brand 2, 20% brand 3. Offers 1 year warranty. 25% for brand 1. 20% for brand 2 and 10% for brand 3. Okay. If you have a question like this, okay, there is no sorry, there is no letters, or they haven't mentioned any events, so you have to mention events before you do the question. Okay, before you answer the question, first define your events. Otherwise, we don't know what are the events, what are the variables you have used. Okay, so first define them. So here they have defined B1 is for brand 1, B2 for brand 2, and B3 for brand 3. R mean repairs. Okay, so uh, uh, so probability of B1, which means this one, probability of brand 1, 0.5 because it is 50%. So 0.5. You know how to convert the percentage to a probability, right? If it is 40%, which means probability 0.4. Okay, percentage divided by 100, you can get the probability. Probability multiplied by 100, get the percentage. Okay. Okay. So R is the repair. So what does this mean? Probability of repair given brand 1. Okay. B1 is the brand 1. Clear? So all probabilities they have given, these are given. Okay. In this slide, you can see these values are given. Okay. So what you need to find is brand 1, probability of brand 1 DVD player and will need a repair, which means you need to find probability of brand 1 mean B1 and intersect a repair R. Okay, so you need to find probability of B1 intersect R. Okay, to do that, simply you can apply your conditional probability here. Probability of probability of repair given B1 equals probability of repair intersect B1 divided by probability of B1. Okay, so using this you can find, because you know this one RB1 it's given and B1 also given, so cross multiply, isolate probability of R intersect B1, plug the values and you can get the answer. Okay.
Hello, sir.
Yes.
So what's the main difference between probability of R given B1 and probability of B1 intersecting R?
What do you mean by that? I didn't get your question.
So
Could
what is
you
the
please
difference
repeat it?
between probability of R given that B1 and probability of B1 intersecting R? So what
Okay.
is the
Okay. Intersect mean they have a common space like this. Okay. This piece. Okay. That's we call an intersection, which mean they have something in common. But given mean something like this. This is my event. Let's say this is my event capital D, and this is my event. Let's say capital. Let's say this is capital A. So given mean, okay, it can be on top of that or like this, okay. It can be anything like this, but so in this case, I need to find the probability of A. But the problem is A is not like A is not alone. It's defined on top of something. It is like very simple example. If you consider event for the experiment rolling a die, consider the experiment rolling a die, and I'm calling an event like even numbers. Okay, event A is even numbers, and again I define another event C, which is even, which is 2, value 2. Okay, then if I need to find the conditional probability or what's going on with this given event, then simply we can use this idea, which is something is already given. On top of that, we define something else. Something else means event. Okay. So we cannot talk about probability of A without talking uh, event D. Okay. Clear?
Yes, sir. Thank you.
Okay. 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 Mutually exclusive event. I already told you. If two or more, let's say two events, if two events, if they don't have any common space or common events, common outcomes, then we call that partition, which mean AIs are mutually exclusive. This is my partition space. These are closed spaced. Okay. So these are my A1, A2, A, K. Okay. Uh, if they have no common outcomes, then we call they are mutually exclusive. See, they have no common outcomes. So events, AI events, AK, A1, they are mutually exclusive. Okay. So consider these events, these mutually exclusive event. If they are exhaustive, if they are complete in the space, okay, see this sample space consists of AKs only. I mean AIs only. Okay, A1, A2, A3, whatever, but only event AIs. Okay, then at least one AI must happen, which means one event should happen. Okay, if my event consists of AIs, then definitely something should happen, right? One, at least one should happen. That's mentioned here. At least one must happen. Okay, if I have only AIs. Okay, so at that point you can simply write union of these partitions is equal to S, right? See, union of these partitions, it is equal to S. This 42. Law of total probability. This law, it is something like ground rule uh, to develop, to discuss our probabilities, because uh, everything in probability is defined on these laws. So this law for total probability. Okay, if we have again, if we have mutually exclusive events, mutually exclusive event, these events are we call A1, A2 up to AK. Okay, that can be any events, that's fine, but your sample space consists of these mutual exclusive events. Okay, then for event B, any event B, we define any event, let's say B, probability of that B we can find using this equation, summation of summation of probabilities that happen, probability of B happens in each piece, each AI. Okay, so this is the, do you remember this part? This is, forget about I for a moment, forget about simple I. This piece mean B intersect A, or simply A, probability of A intersect B, right? So probability of intersection for each different AIs, collection of that we call probability of B. I'll show you that. Give me a second. I'll draw it for you. Again, we have our partitioned space. They are mutually exclusive. They don't have any events in or any values in common. Okay, so check this one. Let's say okay, this one and this one. Do I have any colors? Okay, I don't know whether you can see this color. Can you see blue color? Oh yeah. Okay, these are my AIs. Okay, these are my A1, A2, AK. Okay, AIs. So my event B, I define something like this. This is my event B. This is my event B. So you can see here, as you can see, event B has intersection with, let's say, this piece A3, A3, or let's say A5, A4, right? So they have intersections with event B. At that point, you have to calculate given probabilities. Okay, probability of B given this piece. This piece, let's say, this, what happened? Sorry. So probability for in this AI, this is my B. So what happened with this A1? What happened with this A2? Something like that. Okay. B given A1 and B given A2, something like that. Okay. Intersections. Not only conditional part, intersections. To find the intersection, we need given probabilities or conditional probabilities. That's why conditional probabilities come to play this place. Clear? This is simply probability of A intersect B, not AI. AI is intersect B or B intersects AI. That's fine. Okay, clear? Okay, summation. Okay, don't forget the summation. You have to add each piece. Okay, this is we call total probability. Total probability of a particular event. Total probability of an event. Okay, you can define same for A as well. Okay. Okay, let's check this one. Time is 9:46, right? I think 5 minutes. So, okay, given these values, individual probabilities and conditional probabilities. So what you need to find PA1, those are the probability of selecting 3 workers. Okay, selecting 3 workers, and event B, which is represent the event that worker finished the task before the deadline. Okay, so B is the finish the task before the deadline. So what they need to find, what is the probability that the task will be finished before the deadline by all 3 workers? So all 3 workers mean what? Probability of what? Here workers denote by A. So we have 3 workers, A1, A2, A3. So all of them are, they mean probability of what? Before give me a second. What is the probability that the task will be finished before the deadline by all workers? Yes. So what's they ask? Probability of task will be finished, right? Probability of task. Task we define B, capital B, right? Before the task finished before the deadline, capital B. So we need to find probability of B. To find that total probability, which means you have to calculate each piece for each workers. So probability of probability of task intersect worker 1 plus probability of task intersect worker 2 plus probability of task intersect worker 3, right? So this is the this is equal to probability of B. This is you need to find. Consider each of them, which means you can simply replace them using your conditional probability equation. That's what they have done. Okay, so all values I think given. Once you replace the intersection probability of intersections, then you have this, plug the values, get the answer. Okay, clear?